Hello, and welcome to week 13 of IP 241. I've decided to just hold this class kind of on my own so that you wouldn't have to disrupt your weekend schedules. I know that today is a religious holiday for you, as well as, it's weekend time to spend with your family and so forth. So rather than delay the class until next week, I decided to just record the class. And what I would like you to do is, after you watch the recording, just send me an email and I will give you credit, I will give you the points for attending this week's session. I'm sorry that I missed the class last week. I don't know what happened, but it looked like all of the U.S. professors, or most of us, were locked out of the system, and we couldn't get in for days. And so we finally are in now. Unfortunately, they rectified the problem, or they fixed the problem after it was too late to hold our weekly class meeting. So I apologize for that. But hopefully you'll find just watching this recording will help you with the course content for this week. The first thing I want to do is go over the homework that was last week's homework. The first question was a question saying an experimental addition to Unix allows a user to connect a watchdog program to a file. The watchdog is invoked whenever a program requests access to the file. The watchdog then either grants or denies access to the file. Discuss 2 pros or 2 advantages and 2 cons or disadvantages of using watchdogs for security. So the answer I wrote was, with a watchdog, all file access must first go through the watchdog. So it's a centralized approach. One advantage of a centralized approach is that it may be easier to administer or manage because everything is kind of in one place. As long as the watchdog has not been compromised in any way, any file attached to the watchdog will be secure. But a centralized approach also has its disadvantages. Because all access must go through the watchdog itself is a potential bottleneck and may affect performance. Also, if the security of the watchdog is compromised, file access is compromised as well. So it's a good thing to have it all in one place, but on the other hand, if that watchdog itself gets violated, it has a security flaw in it, and there's a security violation, then all your files would be at risk. So it has its advantages and its disadvantages. This second question I felt was difficult with the amount of information that you were given in your textbook. And the question was, discuss how asymmetric encryption algorithm can be used to achieve the following goals. In authentication, you want the receiver to know that only the sender could have generated the message. For secrecy, only the receiver can decrypt the message. And for both authentication and secrecy, only the receiver can decrypt the message, and the receiver knows that only the sender could have sent it. So the answers, and these are pretty much the same as they were in the instructor's manual. For authentication, the receiver needs to verify who sent the message. If the sender encrypts the message using the sender's private key, the receiver knows that only the sender could have sent it. Okay, so you want to make sure it's the sender, so the sender should encrypt the message with his or her private key. For secrecy, the sender can encode the message using the receiver's public key so that only the receiver can decrypt the message. Now the sender would have the receiver's public key because they're public keys, but they want to make sure that only the receiver can decrypt it. Okay, so the sender would use the receiver's public key so that only the receiver could decrypt the message. And then finally, to achieve both authentication and secrecy, you'd encrypt the message twice. Using both, you do it double encryption, and you would use both the sender's private key for authentication and then use the receiver's public key for secrecy. So it's just a combination of the other two. So to go on to this week, or before I do, let me just say that as you're going through the slides, if you have any questions, just write them down, and when you're done watching the recording, just send me emails with any messages that you might have. Okay? So let's move on now to the learning outcomes for this week. And this week, you're going to look at the principles underlying the Windows 7 design and the specific components of the system, discuss in detail the Windows 7 file system, illustrate the networking protocols supported by Windows. And again, I'm always talking about Windows 7 when I say Windows. Describe the important algorithms implemented with Windows 7, and identify the Windows API equivalents or approximates with the basic Unix or Linux system calls. So Windows 7, it's kind of nice looking at this because Windows 7 is an operating system that most of you are familiar with. And as we go through this chapter, you'll see that it kind of pulls together all the things we've talked about in the operating systems course, but talks about it specifically in a Windows 7 context. So you should be fairly familiar with that operating system. I know a couple of you use Apple, but the majority of the people use Windows 7, which is why they chose it for this course. So Windows 7 uses a client-server architecture to implement the Win32 and the POSIX APIs with user-level processes called subsystems. It's a multi-user system that allows simultaneous access through distributed services or Windows terminal services. The original Windows systems, or even before Windows with MS-DOS and then the original Windows, they weren't really set up for multi-user. Windows itself is set up better for multi-user than some of the earlier versions. They added more and more multi-user stuff to Windows as the Windows operating system matured. Okay, so I'd like to talk a little bit about some of the design principles in Windows, starting with security. Windows uses access control lists to protect the system objects. It uses integrity levels, which are like capabilities that we talked about before. It uses address space layout randomization. And address space layout randomization pretty much prevents attacks on the system by preventing small amounts of code being injected into code that's already loaded in a process. Okay, what it does is it kind of randomizes the address space by putting the code, all over in memory, and so it's not easy for somebody to inject a virus in the code itself. It uses non-executable stacks and heaps, and here it actually uses hardware to mark the stacks and heaps so that they can't be used to execute code. Remember we talked about the buffer overflow problem last week? Well, using a hardware that will prevent stuff from being executed from the stack or the heap will help prevent that problem. It uses encryption, which we've talked about, and it uses digital signatures. So digital signatures are used to sign operating system binary code so that we know that it's the operating system that's executing, and it is code that came from Windows, or from Microsoft, I should say. So that's one way that it tries to protect the operating system as well. So it's designed to be secure. That doesn't mean that a hacker can't get in, that there aren't viruses and so forth that have impacted the Windows 7 system. But as time goes on, the hackers learn new tricks, and then the Microsoft developers learn what to do to prevent those kinds of hacks. It's also designed for reliability. Just in general, Windows has become more and more reliable over the years due to code maturity. The code gets older, more and more bugs are fixed in the code, extensive stress testing on the system, improved CPU architectures, and automatic detection of driver errors. Okay, so that's helped to increase the reliability of the system. But reliability is really fairly challenging because there's more than 1 billion users who run Windows. I think it's something like that. And then there's all the drivers and the applications and the other software that's being downloaded all the time onto the system. So it's very difficult for the Microsoft developers to ensure that everything runs reliably when they have no control over a lot of the things that are actually running on a Windows system. But you can opt to send information to Microsoft to help improve reliability whenever you have a system crash or if your system is performing poorly. You can set up your system so that Microsoft can collect data on your system so that they can then use that to help improve the design and implementation of Windows 7. Windows also has both Windows and POSIX application compatibility. The compatibility layer, when we look at the architecture of Windows, you'll see that it provides support for previous versions of Windows, and also it has a POSIX subsystem that provides POSIX or Unix compatibility. That the POSIX part of it really isn't used very much. But it is there that you can use it. I mean, their goal is to be compatible, application compatible with the POSIX or Unix operating system. Another goal is high performance. It uses advanced local procedure calls for high performance message passing. It uses processor groups to support multiprocessing and user mode scheduling to support task-based parallelism. Okay, so they're trying to get it so that a lot of things can be going on in the system at the same time, giving you higher performance of the system. Some additional design principles. One is extensibility. Windows uses a layered modular architecture with an executive that runs all the kernel mode and server subsystems, and then it has drivers running in user mode so that whenever anyone creates a new hardware device, they can just create a driver that can be downloaded and run on the system. Okay, the layered approach, the modular architecture, is what allows you to use different applications and different hardware devices on your Windows system. Oops, I forgot to point to that one. The next design principle is portability. It's written primarily in C and C++ with few architectural dependencies and very little assembly code. And that's how you can get a Windows system that will run on all these different hardware systems. As long as you have the right type of processor in your system, you can download the Windows operating system and run it. It's not like it only runs on one exact computer system. Like some of the mainframes or mini computers, the operating systems for those computers only run on the hardware provided by that particular computer system vendor. For instance, if you had an IBM mainframe system, you would only be running the IBM operating system on it. You wouldn't be running other operating systems on it. But if you buy a laptop, for example, you can decide to run Linux, you can decide to run Unix, you could decide to run Windows 7 or Windows 8 on the system. And the way you can do that with Windows 7 is because it's designed in such a way that it can run on different hardware. So any laptop that you buy can pretty much run the system. It also provides international support. And of course, you've seen this since I run my system in English, and you probably run your system in Arabic. So you can see that it provides natural language support for the different locales. Energy efficiency, it's designed to extend the CPU idle time by skipping clock ticks, consolidating the software timers, and not using some of the CPUs if it's a multi-core system when the system's not busy, so you don't have all that multi-processing overhead. It also allows dynamic device support, and this is kind of tied into the extensibility design goal, where it'll automatically recognize devices when they are plugged in, and it will find, install, and load the appropriate drivers without user intervention. So, for instance, I have a different keyboard that I load into my system, or I load my headset in to do this call. Microsoft automatically recognizes that, or Windows automatically recognizes that, and loads the correct driver so that I could use that keyboard or use that headset. Okay, so if there are any questions on that, please feel free to email me. Now here's a picture, a nice picture of the Windows architecture, and I won't be going through every block on this architecture, but it's a nice block diagram of what Windows looks like. Down at the very bottom, of course, we have the hardware, and then Windows has this hardware abstraction layer. And the hardware abstraction layer is a layer of software that hides what actual chipset is being used down in the hardware. So it hides the actual specifics of the CPU from the upper layers in the operating system. So everything goes through this hardware abstraction layer with the exception of the virtual memory manager. And they use a certain call to call down to the hardware abstraction layer, and the hardware abstraction layer is really what translates it from whatever the software call was that the upper layers made to the actual call for that particular CPU. So it just provides a layer of abstraction here so that these upper layers in the operating system, or even up at the application level, don't need to know exactly what hardware you're running on. Then we have the kernel, and we've talked about the kernel quite a bit because the kernel is what's responsible for the thread scheduling, the low-level processor synchronization, the interrupt and exception handling, and switching between user mode and kernel mode. And we've talked a lot about what's in the kernel because that's kind of the basis of the operating system, of any operating system. And then we have the executive, which the executive provides all the services that all the things above the executive use in the system. So if you're running a Win32 application or whatever, it goes into the executive, and the executive is what provides things like the object manager, the virtual memory manager, the process manager, the procedure call facility is there, the I/O manager, which includes your file system, your cache manager, your device drivers, that type of thing, your cache manager, as I said, and then a security reference monitor as well. And I'll be talking about some of these, but not all of them in detail. So that's just a nice picture to keep in mind. And then above the kernel is your actual environment where you have what takes care of logging on, takes care of what types of applications you're running, so that there's a special environment for POSIX applications, or a Win16 environment, or OS2, which no one uses OS2. I don't know if you guys even know what OS2 is. Maybe a couple of you who are closer to my age might know, but the younger people may never even have seen an OS2 system. But anyway, all those different environments run on top of the Win32 subsystem, which then talks down to the executive. So I'm going to talk a little bit now about the kernel. And you're actually familiar with all of these things now because of all the different things that we've talked about in the course. But the kernel has four main responsibilities. It's responsible for thread scheduling. And scheduling, as you know, occurs whenever a thread enters the run state or the ready state, the wait state or the ready state, when a thread terminates, or when the application changes a thread's priority. It's responsible for the interrupt and exception handling, which we've talked about. It's responsible for the low-level processor synchronization, and it's responsible for recovery after power failure. One of the things that we have in the kernel is something called the Kernel Dispatcher, and the Kernel Dispatcher is a piece of software that's, rarely paged out of memory because it's busy doing everything that the operating system needs done in one way or another, and it's never preempted. It will never get preempted by some other process. It's always running, or almost always running, because that's what the operating system needs to do all its work. And if you look at what the kernel dispatcher is responsible for, you can understand why it would never be preempted or paged out of memory. It's responsible for thread scheduling, for context switching, for implementing the synchronization primitives, for the timers, for the software interrupts, and for the exceptions. So the dispatcher is using a 32-level priority scheme to determine the order of thread execution. It has the high-level and low-level threading, so it does all this thread scheduling and deciding when each thread should be scheduled. And then it has all these other things like the context switching, switching between different threads or different processes, implementing things like semaphores and mutexes that we've talked about, timers, so that if you have quantums that are being scheduled, or it's just keeping track of how long some process is running, all that the kernel dispatcher is responsible for, as well as interrupts and exceptions. So it's pretty much needed for just about everything that goes on in your system. So to talk a little bit about the scheduling, I mentioned that the kernel is responsible for that. Realize that each process has one or more threads, and we talked about that. We talked about processes and threads in operating systems. And each thread has a scheduling state. It could be ready, it could be standby, it could be running, it could be waiting, it could be in transition, or it can be terminated. It has a 32-level priority scheme, which I've already mentioned. The priorities are basically divided into two classes. The real-time class contains the threads with the priorities from 16 to 31, and the variable class contains threads having priorities 0 to 15. So it uses these different priority levels to determine the order of thread execution. It has processor affinity, and so that says, okay, what processor should this thread be assigned to if you have a multi-core system? So processor affinity pretty much refers to assigning or restricting a thread to run on a particular core or CPU. And then the thread also keeps track of its utilization. So CPU utilization is tracked using a hardware timestamp counter so that you know every thread in the system, how much CPU is it using, and that can be tracked and dealt with. The kernel has dispatcher objects, and it's these objects, Windows is pretty much an object-oriented system. There's objects that are used at the different levels, so you'll hear objects being talked about throughout the Windows operating system. It has dispatcher objects which control the dispatching and the synchronization in the system. And so these are some of the different types of objects that it has. It has an event object, and this would record when an event occurs and synchronizes it with an action. The keyboard's pressed, or that kind of thing could be considered an event, and then there's some action that the operating system takes. A mutant is provides kernel mode or user mode mutex. A mutex is a kernel mode only mutual exclusion mechanism. it provides the semaphore objects, and they control the number of threads that can access a resource. And of course, there are thread objects, which are scheduled by the kernel dispatcher and associated with the process, and timers that keep track of time and signal the timeouts. Another thing that the kernel has is responsibility for software interrupts. With the kernel, you can see that it has what they call asynchronous procedure calls. And so an asynchronous procedure call will break into an executing thread and call a procedure. It's used to run a new thread, to suspend or resume a thread, to terminate threads or processes, to deliver notification of I/O complete, and to get the contents of the CPU registers for a running thread. So this is, when it has to get in there and do something, it will do an asynchronous procedure call. There are also deferred procedure calls, and this is a way that the kernel can postpone non-urgent interrupt processing. The asynchronous was used for more the urgent interrupts. The non-urgent, they don't have to be handled right away. So, anything that the operating system can defer till later, it will postpone by using a deferred procedure call. So it's kind of like when the operating system has time, it will do these things. And it's also used to do things like timer expirations and preempt thread execution at the end of a scheduling quantum. Okay, those are not urgent things, notifying that a timer expired, whether you get it 1 millisecond later isn't really going to affect the system with a timer, or if it doesn't get to it right away, getting a process out of the CPU. As these deferred procedure calls, even though they're called deferred and will happen later, we're not talking hours later. We're talking, little bitty time, a little small amount of time later that it will get to these. It just doesn't do them immediately. So they'll get to it eventually, but it's not an instantaneous thing. And so it's used for things that aren't that important for the operating system to handle immediately. Your book also talks about the exceptions and interrupts, and what the kernel does. And again, these are responsibilities with the kernel dispatcher. The kernel dispatcher provides trap handling for exceptions and interrupts generated by the hardware or software. Exceptions that cannot be handled by the trap handler are handled by the kernel's exception dispatcher. So exceptions in kernel mode cause the exception dispatcher to create an exception record and find an exception handler to deal with the exception. An exception in user mode sends the exception to a debugger port if registered, or finds an exception handler to deal with the exception. And then there's an interrupt dispatcher, handles the interrupts by calling the proper interrupt service routine from the interrupt dispatch table. And we've talked about these before. So these are some of the things, again, that the kernel is responsible for. As I mentioned, it's also responsible for switching between user mode and kernel mode. And if you recall, each thread in Windows is actually 2 threads. There's a user mode thread and a kernel mode thread. When a user thread requests a system service, it causes a trap to go to kernel mode. Okay, so you're in a user mode thread, you need to use some service of the operating system that will actually cause a trap, an exception, and that then handles the request to go to kernel mode, to actually get to those system calls, the actual, get down to the low levels of the operating system and finally down into the hardware. So the kernel trap handler is what switches between the user thread and the kernel thread, and then after the kernel mode processing is done, the kernel layer is called then to switch back to the user thread. And we've looked at this before, but it's just, to realize how it is in the Windows operating system where we have a user mode thread and a kernel mode thread. Okay, so that's kind of what I wanted to just highlight. We've talked about these things in great detail, just generally throughout the course, and so that just gives you an idea of specifically how does the Windows kernel handle things. And your book, of course, goes into a lot more detail than I'm able to do so in this particular session. So to continue then, if you have any questions on the kernel mode, please send me an email, let me know, and I will address them through email. And if it's a question that I think more than one person might be interested in hearing the answer to, I will post them to the Week 13 discussion board as well, so everyone can see any questions that were asked and answered. Okay, and you could feel free to post your questions to the discussion board as well. I do check that every day, as long as they don't lock me out of the system again. So let's talk about the executive. This is something that we haven't talked about specifically, but when we get into what the executive does, you'll recognize a lot of these concepts because we've talked about them. So the executive provides a set of services that all the environmental subsystems use. And remember, the environmental subsystems were the Win32 system, the Win16 system, the OS2 system, the POSIX system. Those things were the environmental subsystems. And the executive provides the services. Our applications run on top of these environmental subsystems, so we call things, the environmental subsystem then calls into the executive, which calls down to the kernel, which calls down to the hardware abstraction layer, and so forth, because we have this layered architecture. So calls that we make in our programs or in our applications are actually going to the executive, and that handles all these different services for all the different environments, and kind of translates it down to the specifics in the Windows kernel. So we have an object manager, and the object manager manages dispatcher objects, which I just talked about what they were in the kernel. That would be the threads, the processes, the events, the mutexes, the semaphores, files, sections, ports, and internal I/O objects. And each object has a handle which can be used to access that object. And that's important to know because we'll see that when we look at some of the APIs. There are APIs where you're getting the handle to a certain object. So that's kind of like the identifier for these different system objects. The virtual memory manager manages the virtual address space, the physical memory allocation and paging. And remember, we talked about all this for a couple weeks when we talked about memory management. So the way Windows does virtual memory allocation is it first reserves one or more pages in the virtual address space, and then it commits the allocation by assigning the virtual memory space to the actual physical memory. So it's kind of a two-step process saying, first I'm going to reserve it, then I'm actually going to assign that physical memory space to this process. Remember we talked about page tables way back when, and the virtual address translation in Windows uses a multi-page table, and your book goes through this. But remember, we looked at how if you have a big memory space, you wouldn't have enough room in a page table to keep the whole thing in memory, so it goes to this multi-level table where you have a page directory entry which goes to a page table entry, which then will point to the different pages and so forth. And so you have different levels of page tables before you get actually down to the pages in memory. It also has a process manager, and the process manager is what provides the services for creating, deleting, and using processes, threads, and jobs. And your homework will actually talk about some of the APIs. You're going to look at some of the APIs that are used to do this process management. But the process manager is responsible for doing this creation, deletion, and actually using the different processes and threads, and what Windows calls jobs. Processes contain one or more threads, and then the processes themselves can be grouped into jobs. And these job objects are used to limit CPU usage, to limit the working set size, and to work with the processor affinities. In other words, you can say, well, I have a certain job, and all the processes from that job should be run on a certain CPU, for instance. So you can kind of group the processes together into jobs and manage them that way, where every process in that job gets, has certain characteristics. Or you can manage the individual processes, or you can manage the threads within a process. It uses the advanced procedure calls to start, suspend, and resume threads, to access the thread register, to terminate threads and processes, and it also provides debugger support. The executive also contains the facility to do client-server computing, because all the environmental subsystems, the user authentication system, the network facilities, printer spooling, web services, the network file system, the plug-and-play, they all use kind of a client-server architecture and are doing message calls, between these different components in order to do its work. Okay, because everything's modular, you're not directly accessing anything. Instead, what you're doing is you're going through and you're, actually doing kind of a system call or a message passing kind of scheme, sending a message to whatever component in the system is responsible for that particular activity. Okay, so it does a lot of message passing, and that's why it's important that message passing is high performance in the system, and so you need to realize that all these different subsystems, the user authentication, the networking, and so forth, they all use the facilities for client-server computing. Okay, so Windows Win32 has different kinds of message passing services that it uses. The network manager, or the I/O manager, is what's responsible for managing the file systems, the device drivers, the network drivers, and the buffers for I/O requests. Okay, so all those things that we talked about when we talked about the file system and we talked about the hardware, when you actually say to read a file in your Windows program, for example, that request will go to the I/O manager, which will then call into the kernel and so forth to get down to the actual hardware devices for input and output. And then there's the cache manager, and that works closely with the virtual memory manager to provide the cache services for all the components that are under the control of the I/O manager. So if you're caching things as they're being read from disk or whatever, the cache manager will be involved. The executive also includes a security reference monitor, and this is what provides a uniform mechanism to perform runtime access validation and audit checks on every access. So it checks the security token and the access control list to ensure that the user process is allowed to access the object. And we talked about, security in general in operating systems, and we talked about different ways that that's done. And so in Windows, it has the security reference monitor that takes care of all this security checking. We've mentioned the plug-and-play. The plug-and-play manager is used to recognize and adapt to hardware changes. That's why I can just plug in my headset when I need it and unplug it when I'm not using it, for example. The plug-and-play manager takes care of that. And you're probably very familiar with that, even if you just plug a flash drive into your system. You see the plug-and-play manager come into play. The power manager, because Win32 or Windows 7, I should say, is run a lot on laptop kind of computers. It has a power manager that'll detect the system conditions, and it tries to improve the energy efficiency. And you can also configure different things using the power manager so that your laptop can use its battery most efficiently. It's mostly, even though it does improve energy efficiency when you're plugged in, it does even more of that when you're in battery mode on your system. So it also manages sleep and hibernation. And I don't know if you do this on your system, but I do it all the time if I'm not using my system. Rather than powering it down, I just put it into sleep mode or into hibernate mode. So it's a very fast process. When I get back to the computer and want to do something, I just, they just wake it up pretty much, and it comes right back up, and everything's there that I was working on when I left the system. And then there's the configuration manager, and that's what manages the system registry information, the default user preferences, the software installation, the security, and the boot options. So you're probably kind of familiar with these functions in Windows 7. And then this is just kind of identifying, and in your book it actually goes into a lot more detail on each of these, on what it does, and relates it to the operating system concepts that we've learned. Okay, any questions on what the executive does? Again, if you have any questions, please send me an email or post it to the discussion board, and I will respond to your questions. Okay, the next thing your book talks about is the Windows file system. Windows uses a volume structure in the file system, and this comes out of the NT version of Windows, and so it's called NTFS. NTFS uses clusters as the underlying unit of disk allocation, which results in less fragmentation than the older Windows file system, which used something called FAT, which was the file allocation table. Every file is described by records in an array stored in the master file table, which is called the MFT. There are other files that are used in the file system, like the recovery file, the log file, the volume file, the attribute definition table, the root directory, the bitmap file, the boot file, and the bad cluster file. So all the file system data structure updates are performed inside transactions that are logged. Before a data structure is altered, it writes a log record to one of these log files. And then the transaction writes a record that contains the redo and undo information. So that's how, if an error occurs or a crash occurs, you can sometimes get back to where you were before. So after a crash, the file system data structures can be restored, maybe not to where they were right when the system crashed, but at least to a known point where it will all be stable, rather than being in some kind of state that the operating system can't deal with it. So it doesn't guarantee that all your user file data can be recovered after a crash, but it tries to ensure that the file system data structures are undamaged and are consistent after the crash. The log file is stored in a metadata file at the beginning of a volume, and then the Windows 7 log file service is what provides all this logging. Okay, so there are all these different files. There's the the master file table, the log table, the recovery table, all these are actually files that the system uses to actually manage the file system itself. With the Windows file system, it manages security based on the Windows 7 object model, and we talked about that a little bit, but volume security, there's a security descriptor attribute that contains the access token of the owner of the file and access control list listing the access privileges that are granted to each user. So it's kind of, Windows has this whole object model. The volume security is just an extension of that, and then this describes specifically what the object model, how the object model is used to provide security for the operating system. So we're again using this idea of having an access control list, and that helps determine who can access each individual file. Okay, they have the Windows file system. Oh, let me get my pointer here, I forgot. The Windows file system also includes a fault-tolerant disk driver, which can be used to combine multiple drives into a logical volume, and this is done, of course, to improve performance, capacity, and reliability. And so your book goes into quite a bit of detail on, FTDisk, which is the fault-tolerant disk driver for Windows 7, and it talks about how it does this, how multiple disks can be used to create a large logical volume in the Windows file system, how physical partitions can be allocated. Excuse me, I need to take a drink. How physical partitions can be allocated to perform a stripe set, and we talked about striping when we talked about RAID, when we talked about file systems, and so it does basically the RAID level 0 or the disk striping on the system. And it also provides RAID level 1, which is the disk mirroring. It deals with the sectors that go bad, using a thing called sector sparing and cluster remapping. Let's see what else. There are just a number of things that the disk driver does. Okay, so it goes into it in a lot more detail in your book than I really have time to hear, but it's something you probably want to read about. It also has the capability, the Windows file system has the capability to perform data compression on a single file or all files in a directory. That should say directory, not director. I'll fix that. And you probably have done this, or you may have done this if you start running out of drive space. You compress your hard drive. And so it'll compress it into compression units, which are blocks of 16 contiguous clusters on the disk. Windows also supports mount points, symbolic links, and hard links. I don't know if you've used any of those, but you can do that where you can kind of mount volumes at certain mount points and have symbolic links to them and so forth. Windows keeps a journal that describes all the changes that have been made to the file system, which I kind of mentioned before. And it also allows for a shadow copy of a volume that can be used for recovery. Of course, many of us on our laptops, we don't have a shadow copy of a volume. We don't have data that's that critical that we have to have it mirrored like that. But of course, if you were using Windows 7 for running a big, server farm or something like that, you may use something like shadow copies to make sure that the data is good. even if there's a crash or whatever, you can always recover from the mirrored volume. All right. Windows also provides a number of things for networking support, and so it supports the peer-to-peer networking, it supports client-server networking, and it supports network management. Under the networking, it provides data transport, inter-process communications, network file sharing, and remote printing, and you've probably used most, if not all, of these at one point or another when you're working on a Windows 7 system. When we're talking about data transport, we're talking about the transport protocols that are implemented as drivers. You're probably already familiar with things like TCP/IP or HTTP, because we use those all the time when we're working just with the web, which is what most of us do with our computers anymore. It also has some other protocols like SMB, that's the server message block protocol, and that sends I/O requests over a network. Let's see, I talked about TCP/IP, you're already pretty familiar with that. There's the PPTP, which is the point-to-point tunneling protocol, and that's used to communicate between remote access servers running on Windows machines. HTTP you're familiar with, that's used to go to the web. Then they have something called a web distributed authoring and versioning protocol, and you would probably use that if you were into web distributed authoring or collaborative authoring across a network. It also supports name pipes, which we've talked about in this class, and remote procedure calls. And with the remote procedure calls, it uses the distributed computing environment standard for the remote procedure call messages, so that any programs that are written to use Windows 7 RPCs, remote procedure call, are very portable. Your book also goes into the redirectors and servers that are used to access a remote computer as if it was a local computer, and you may have done this sometimes when certain companies, including Microsoft, will ask if they can, open your system. If you could open your system up so that they can access it as if they were looking at it locally, and they'll use that to help them debug a problem. Then it has also Windows Domain. The Windows Domain is a group of Windows workstations, and again, you wouldn't be using this in your home environment, but in a company, you might have a group of workstations and servers that share a common security policy and a common user database, and that's called the Windows Domain. And then it also uses LDAP. Active Directory in Windows uses LDAP, which you may be familiar with if you've taken other courses. That's the Lightweight Directory Access Protocol. That's used for things like company directories and phone book lookups and so forth in a system. And so Active Directory uses LDAP, which is fairly standard in the industry. Okay, now to talk a little bit about the Windows API. And your homework questions have to do with this. I know I'm close to running into my full hour here, but I'll continue through all the charts, and you can again access the recording at your leisure. The Win32 API is the programmer interface to the capabilities of Windows, including an interface to the kernel objects, how it shares objects between processes, how it does process management, how it does inter-process communication, and memory management. And generally, when we're accessing these kernel objects, the application programs use usually a create XXX function to open a handle to an object. Okay, so it really depends on what type of object you're creating. Like if you're creating a process, you'd use a create process function to open a handle to a process object. Okay, so the XXX is just a shorthand for the different types of objects that you might be accessing, and then you use the close handle to release or delete an object. Okay, and it depends on what kind of objects that you're working with. So to access kernel objects, you use the create and then to actually get a handle to an object. And remember, the handle is the way you're identifying these different objects that are down in the kernel, and then you use the close handle when you're done with it. The Win API also has function calls for sharing objects between processes, and Windows has 3 ways you can do this. A child process can inherit an object from the parent by using the create and create process APIs. Okay, so the parent may be creating a child process, and then the child process can be inheriting some of the objects that the parent process was using. Another way you can share objects is if one process, I should say, gives an object a name, another process can open it by name, and of course one process has to tell the other process what the object was named. And then if one process creates a handle to an object, a second process can open the first process, and then, because remember, a process is just an object on the system, and then use the duplicate handle API to duplicate the handle to the object that it wants to access. Okay, so that's pretty much the different ways that you can use the APIs to share objects between processes. Now this next slide is fairly important, because this is the one that talks about some of the things that your homework question asks. This is what APIs are used for process management. Some of the process management APIs that Windows uses are the create process API is used by a thread to create a process. And then there's also the create thread API is used to create a thread. So you can create processes and you can create threads. Remember, it seems funny that a thread is creating a process, but remember that every process has that initial thread, and so that initial thread would be creating the additional threads or be creating new processes. The set priority class API is used to change the priority of a process, and then there's a set thread priority, which is used to set the priority of a thread within that process. A thread can be suspended using the suspend thread API, or it can be resumed using the resume thread API. And then threads can be synchronized. Remember, we talked about synchronization and how we looked at kind of a fork and exec and how that worked to synchronize processes. Well, in Windows, you get synchronized threads by using the wait for single object or wait for multiple objects API, or by using critical section APIs like initialize critical sections, enter critical section, and release critical section. And we talked about critical sections in general. Now you know what APIs you need if you're actually writing those things in Windows. And note that there are a lot more APIs used to manage processes and threads in Windows. The book just gives you kind of a few of them that you might be interested in, that relate kind of to some of the different things we've talked about in our previous classes. Whoops, I skipped two. Okay, Windows also has APIs for inter-process communication, and this can be done using shared kernel objects or the window messaging facility. Okay, and when you use the window messaging facility, you'll use APIs like post message, post thread message, send thread message, and send callback message kind of APIs. And that's how we can get different processes to talk to one another. And then memory management. That includes the APIs for virtual memory, where you're allocating virtual memory, freeing virtual memory, or locking virtual memory, and that would be the virtual alloc, the virtual free, and the virtual lock APIs. It has APIs for creating memory map files, which is the create file mapping API. For heaps, you can manage heaps, you can create heaps, you can allocate memory to heaps, you can reallocate memory to heaps, you can work with the heap size, free the heap, destroy the heap, lock the heap, and unlock the heap. And then thread local storage, and that's a TLS is what the API is. It looks kind of like a capital I, but it's TLS, thread local storage. It's the thread local storage, allocate, free, set value, and get value. So these are just a subset of all the different APIs that Windows has. So your homework for this week, let me move on to the next slide. Your homework for this week is asking about how processes are managed. So it says, how are processes managed in Windows? Identify 3 Windows APIs for process management and their equivalents in Java and POSIX. Now be sure that you go out and read the information on the course website for week 13. There's actually, usually it just has a short introduction to what you're going to cover in the week. This week, it has a lot more information out there. So be sure to go out to our course website and read the information that's out there for week 13, as well as the information in your textbook for the APIs for process management. Then to complete the assignment, first describe how processes are managed in Windows. Just describe it in general, the things you know about process management, and what you might have learned this week in more detail about the process management in Windows. And then choose 3 APIs that are used to manage processes or threads, and identify APIs in POSIX or Unix and Java that do, APIs that do the same thing as those APIs in Windows. For example, you can list the APIs to create a process, to end a process, and create a thread, and give me the API for how to do it in Win32, how to create a process, end a process, and create a thread in Win32, how to do that in Java, and how to do that in POSIX. Now you may not be able to find all that information in your book, so I know you're going to be searching the web for that. If you use other web references or other books, just include the web pages you used or the books that you used to complete your homework assignment, just so I know that you've looked at kind of a reputable source in finding the information. Okay? So you want to first, remember it's a 2-part thing. First you want to describe in general how processes are managed in Windows, and then you want to give me 3 APIs for managing processes or threads, and tell me the API, and all I need is the actual procedure call, like create process or create thread. Tell me how you do 3 different tasks to manage processes. So I gave you examples of doing create a process, end a process, and create a thread, but you can pick other things and look for the APIs to them. These 3 are just pretty easy to find, so I listed those. Okay, so that's the homework assignment for the week. Again, make sure that if you have any questions, you email me or you send me any questions using the discussion board. Either way, I will respond to your questions. And again, this will be due on Sunday. I know that only gives you a couple of days, but you can turn it in until Tuesday without any late penalty. Okay, any questions on that? Okay, again, if you have questions, just send them to me. I did do a quick quiz for this week. So you can look here. Here are some things. Do you remember we just went over all of these things? Can you describe at least 3 of the design goals of Windows? I gave you a whole list of the design principles for Windows. Can you describe 3 of them? Tell me what an object manager does, or you don't have to tell me. These are just for your own use. What are the 4 main responsibilities of the kernel? Describe 3 ways objects can be shared in Windows 7, and name 3 of the transport protocols that Windows supports. It supports more than 3, but just name 3 of them. Can I just talked about all of these things. Can you remember any of it, or at least look through the slides of your textbook and see if you know these things? Again, you don't have to send me your answers. This is just something for you to do to see how much did you understand or how much did you remember of what I just talked about. Okay, and so I'll send you a PDF with these slides, and then probably tomorrow I will send out the answers to the quick quiz, just if you want to check yourself. Or actually, I may not do it tomorrow because I don't know whether you're going to have a chance to watch the recording by then. But I will send them out later in the week so you can check your answers. Again, after you've watched this recording, please just send me an email so that I know you've watched the recording and I can give you the attendance points for this week. Okay? I'm sorry we didn't get to hold our last class session in person. This is really the last scheduled class session for the term. You can always email me, and if for some reason you want to, talk to me, we can always go into our Blackboard Collaborate session that we have out there and talk about things. But as far as I know, this is the last week that we have of classes. Now you do your review for your final exam and take the final. And again, I've asked a number of times about the review guide or the study guide for the final. I still have not received that. I still have not received the midterm exams. I don't control either the midterm exam or the final exam. But as soon as I get any information on any of that, I will forward it to you immediately. Okay? So if you have any questions on anything I've talked about in the entire semester, please feel free to contact me. Let's see, I don't know how long I'm going to have access to the SEU system once the class formally ends. They haven't told us any of that. But if there is anything you need, you can email me, at least until I lose my email access to the SEU system. And I did email you from my Franklin University system as well, so you can always use that as my email if you can't get in touch with me through the Saudi system. Okay. I guess that's everything. I want to thank you all for your patience and putting up with me this semester. I know we've had some hard times because of different expectations and how I do things a little differently than what you're used to. I want to thank you for all your hard work, and I wish you luck on the final exam and in your studies after you complete this class. All right, so that's all I have. I feel kind of sad just saying goodbye like this, but I hope all goes well for you. Bye-bye.